Partial fractions. Partial fractions for irreducible factors. Objectives. 1. Partial fractions of a proper rational fraction f of x divided by g of x when denominator contains only non-repeated irreducible quadratic factors. 2. Partial fractions of a proper rational fraction f of x divided by g of x when denominator contains both repeated and non-repeated irreducible quadratic factors. 3. Partial fraction of an improper rational fraction f of x divided by g of x. Partial fractions of a proper rational fraction f of x divided by g of x when denominator contains only non-repeated irreducible quadratic factors. Suppose we have a fraction with denominator containing non-repeated irreducible quadratic factors. For the factor a1x square plus b1x plus c1, we write capital A into x plus capital B whole divided by a1x square plus b1x plus c1. For the factor a2x square plus b2x plus c2, we write capital C into x plus capital D whole divided by a2x square plus b2x plus c2. Illustration. 2x plus 1 whole divided by x minus 1 into x square plus 1 split into partial fractions. Solution. Let us take down the given fraction. The denominator contains the factor x minus 1, which is a linear factor, and the factor x square plus 1, which is an irreducible quadratic factor. For linear factor x minus 1, we write a divided by x minus 1. For irreducible quadratic factor x square plus 1, we write b into x plus c whole divided by x square plus 1. Take this equation as 1. On cross multiplication on RHS, a into x square plus 1 plus b into x plus c into x minus 1 whole divided by x minus 1 into x square plus 1. Eliminate the denominators and write down the numerators. On LHS, 2x plus 1. On RHS, a into x square plus 1 is written as a into x square plus a. bx plus c into x minus 1 is written as bx square minus bx plus cx minus c. On combining x square coefficients, x coefficients and constant terms together, we get 2x plus 1 is equal to a plus b into x square plus minus b plus c into x plus a minus c. On comparing x square coefficients, we get a plus b equal to 0. On comparing x coefficients, we get minus b plus c equal to 2. On comparing x square coefficients, we get a minus c is equal to 1. On solving these three equations, we get the values a equal to 3 by 2, b equal to minus 3 by 2, c equal to 1 by 2. On substituting these values in equation 1, the given fraction can be written into partial fractions as 3 by 2 whole divided by x minus 1 plus 3 by 2 into x plus 1 by 2 whole divided by x square plus 1. Partial fractions of a proper rational fraction f of x divided by g of x when denominator contains both repeated and non-repeated irreducible quadratic factors. Illustration. 3x plus 1 whole divided by x square plus 1 whole power 2 into x square plus 3 split into partial fractions. Solution. Let us take down the given fraction. The denominator contains the factor x square plus 1, which is irreducible quadratic factor, repeating twice, and the factor x square plus 3, which is a non-repeating irreducible quadratic factor. For repeated irreducible quadratic factor x square plus 1, we write a into x plus b whole divided by x square plus 1 plus c into x plus d whole divided by x square plus 1 whole power 2 plus. For non-repeated irreducible quadratic factor x square plus 3, we write e into x plus f whole divided by x square plus 3. Take this equation as 1. On cross multiplication on RHS, a into x plus b into x square plus 1 into x square plus 3 plus c into x plus d into x square plus 3 plus e into x plus f into x square plus 1 whole power 2 whole divided by x square plus 1 whole power 2 into x square plus 3. Eliminate the denominators and write down the numerators. On LHS, 3x plus 1. On RHS, simplifying x square plus 1 into x square plus 3, we get x power 4 plus 4 into x power 2 plus 3. Multiply with ax plus b, we get a into x power 5 plus 4a into x power 3 plus 3a into x plus b into x power 4 plus 4b into x power 2 plus 3b, and arrange the terms in a specific order. Multiplying cx plus d into x square plus 3, we get c into x power 3 plus 3cx plus d into x square plus 3d, and arrange the terms in a specific order. Expanding x square plus 1 whole power 2, we get x power 4 plus 2 into x power 2 plus 1. Further, multiplying with ex plus f, we get e into x power 5 plus 2e into x power 3 plus ex plus f into x power 4 plus 2f into x power 2 plus f, and arrange the terms in a specific order. Combining all x power 5 terms. Combining all x power 4 terms. Combining all x power 3 terms. Combining all x power 2 terms. Combining all x terms. Combining all constant terms. On both the sides, comparing x power 5 coefficients, we get a plus e equal to 0. Comparing x power 4 coefficients, we get b plus f equal to 0. Comparing x power 3 coefficients, we get 4a plus c plus 2e equal to 0. Comparing x power 2 coefficients, we get 4b plus d plus 2f equal to 0. Comparing x coefficients, we get 4a plus 3c plus e equal to 3. Comparing constant terms, we get 4b plus 2d plus f equal to 1. On solving these equations, we get the values of a equal to minus 1, b equal to minus 1, c equal to 2, d equal to 2, e equal to 1, f equal to 1. On substituting these values in equation 1, the given fraction can be written into partial fractions as minus x minus 1 whole divided by x square plus 1 plus 2x plus 2 whole divided by x square plus 1 whole power 2 plus x plus 1 whole divided by x square plus 3. Partial fractions of an improper rational fraction f of x divided by g of x. Improper fraction. If degree of f of x is greater than or equals to the degree of phi of x in a rational fraction f of x by phi of x, then the rational fraction is called an improper fraction. If an improper rational fraction f of x by phi of x is given for splitting into partial fractions, on dividing the polynomial f of x with another polynomial phi of x, there exists one more polynomial q of x. The result is another polynomial r of x. It can be written as f of x is equal to phi of x into q of x plus r of x. Dividing with phi of x on both the sides, we get f of x divided by phi of x is equal to q of x plus r of x divided by phi of x. Here, f of x whole divided by phi of x is an improper rational fraction. Q of x is a polynomial, and r of x whole divided by phi of x is a proper rational fraction. Illustration. X power 4 whole divided by x minus 1 into x minus 2 split into partial fractions. Solution. Let us take down the given fraction. Expanding the terms x minus 1 into x minus 2 results in x square minus 3x plus 2. On dividing x power 4 with the polynomial x square minus 3x plus 2, we get the quotient x square plus 3x plus 7 and the remainder 15x minus 14. So, we can write the given fraction as x square plus 3x plus 7 plus 15x minus 14 whole divided by x square minus 3x plus 2. X square minus 3x plus 2 can be written as x minus 1 into x minus 2. Take this as equation 1. Let us take down the fraction, which is a proper rational fraction containing non-repeated linear factors. Partial fraction is capital A divided by x minus 1 plus capital B divided by x minus 2. Take this as equation 2. On cross multiplication on RHS, A into x minus 2 plus b into x minus 1 whole divided by x minus 1 into x minus 2. Eliminate the denominators and write down the numerators. On LHS, 15x minus 14. On RHS, simplifying ax minus 2a plus bx minus b. Combining all x coefficients, we get a plus b into x plus. Combining all constant terms, we get minus 2a minus b. On both sides, comparing all x coefficients, we get a plus b equal to 15. Comparing constant terms, we get minus 2a minus b equal to minus 14. Simplifying these two equations, we get the values of a equal to minus 1 and b equal to 16. Substituting these values in the equation 2 becomes 15x minus 14 whole divided by x minus 1 into x minus 2 is equal to minus 1 divided by x minus 1 plus 16 divided by x minus 2. Replacing this partial fraction in equation 1, equation 1 becomes x power 4 whole divided by x minus 1 into x minus 2 equal to x square plus 3x plus 7 plus minus 1 divided by x minus 1 plus 16 divided by x minus 2.